Hi there, thanks for joining me for another episode. In this episode, we're going to tackle music. So we're going to look at p5.js and how it can look at a MP3 file, pull some data from it, and then we can use our coding procedures to plot that data in an interesting way, graph it in an interesting way. So what you see here playing out is the skeleton form. This is a kind of like a dynamic geometry. It's a sinusoidal wave that's moving through these different sections, different delineations. Those different segments are going to be associated with data from our music. So what we'll do is we'll have the skeleton structure here that's changing in a predictable way throughout the song, and then graphed on top of that form will be the actual data. Whatever changes that we'll make to these geometries will represent the music itself. So we'll be able to see the sound waves being represented through this form here, and I can show you that here. You're not going to be able to hear the sound because one of the things you're going to want to do when you tackle a problem like this is mute everything. When you're first starting out making your visualization, you're doing the mechanics, and that doesn't require that you need to hear the music exactly. It's not until you're fine-tuning your visualization that you need to listen to the music. So the first 1,000 attempts at doing this, you're not going to hear the 5, 6, or 7 seconds of a song that you may like, because at the end of this project you'll hate it. So just mute in the browser, then you don't have to worry about it, or turn your headphones down or whatever you need to do, and then just test it visually. And then once you have it kind of knocked out where you want it, then you can fine-tune it with the music, and it's not going to be such a hard experience. Hearing that music over and over again, I don't care how much you love a song, but just hearing the 5 or 6 seconds, at the very least it will change the song for you. It's not going to be the same afterwards, so avoid that way. So here I'm going to play this, and you can see the data set being described along this structure here. So this is basically what this program does, is it creates a substructure, the sinusoidal wave, and then it plots the data on that substructure. So this is one way of tackling a visualization. You want to not just graph the data plainly, but you can manipulate how that data is moving, how it's being displayed on the screen, if it rotates, or there's all kinds of magical stuff that you can do with this data. So this is a good place to start. So instead of just typing out the program with you and describing it line for line as I type it, I'm just going to go through my annotated file here. This is at GitHub, and you can find a link to this in the description. The very first thing you want to do is get your sound all laid out, and we're going to use some methods and some constructors from the p5.js library to do that. We need a variable to hold our MP3 file. Then we're going to use a preload to upload that asset. So you'll go over here to the sketch, and you're going to upload a file, and then you just drop your sound in there, and it uploads it to the p5.js cloud where it can access that. So once you've done that, then you can start assigning things. So here we've assigned the variable music to that file, so now it contains it. We also need a variable that will hold our fast Fourier transform. This is a constructor in p5.js that will analyze the data. So basically it will go through the sound wave and perform some mathematics to it, and it's isolating different frequencies and the amplitudes associated with those frequencies, and it can sort them out and organize them in a way that is meaningful to us visually. So that's what that does. We want a play button so that we can stop and start. This is going to help us out in testing. It's also a way for the user to interact with the output. Whenever the fast Fourier transform constructor is done, it returns an array, and we want that array to be held in a variable, which we're going to call sound wave. I'm not sure why. Maybe if you know the answer, leave a comment. But when we declare this, we don't have to declare it as an array. We can just declare it as an undefined variable. And then when we associate that, or when we try to define it, p5.js is going to say, okay, we're going to turn this into an array variable, because that's what we need to hold this object. Or the object is an array inside the variable. Whichever way it works out, in the end, we will be using this as an array. So even though it doesn't have, this here, it's going to work like that later on. In setup, we do our buttons. If you want to know how to create buttons, just go to the example page, p5.js. It will explain that to you. They're pretty easy to work out. So you use the dot syntax, the method for that, put in the name that you want, and then somewhere in the global space, you create a function that responds to that. Where are we at here? Okay, we're going to start our music in setup. So as soon as setup goes, it's going to activate play. It's going to play this music file. When it's playing, then we can perform this action here. I'm not sure if you have to play the song to do the fast Fourier transform or not. I haven't tested that. but this is just the order of things that I was shown, and I just go with it rather than trying to reinvent the wheel. So if that's the case, you'll find that out, but if not, just do it this way, it's fine. In our fast Fourier transform parameters, we need a couple arguments, some variables here. We need one that accounts for the smoothness. So when it's averaging things out and it's kind of bifurcating the data. So you can get a rigid return of that, or you can get kind of a fluid, very relational set of data. Depending on, this is a coefficient, so it can be 1 or less than 1. So I have it at about 2%, 2.5% of that coefficient, which for me, it just increases the speed. I don't need the smoothing so much. So I just have that to keep the speed down, or to keep the processing costs down so that it moves faster. This number here is the number of bins that you have available to sort out the amplitude values. This has to be a factor of 2, so like a multiple of 2. So 2, 4, 8, 16, 32, 64, 128, 256. The higher that number, the slower it's going to be. So 64 is a pretty good range for our amplitudes, and if that number sounds familiar, that's kind of what you have on an electric keyboard. Is like 64 keys is usually the standard. So it's like a good range to cover the sound that we need. Next, we need a function that's going to handle our visualization. So we're going to do some stuff in Draw that's going to set up how things are visualized, and then we're going to have a function that actually does the output and performs a calculation. So we need that here. I've made up the name Visualizer for this function, and then down here in the global space, I've created that function. It also has a method inside called update, and update receives 2 variables. It's going to receive the number of the bin that the amplitude frequency is in, so in other words, the index value of the spectrum that we're analyzing, and it has the amplitude, or the value inside that element, that bin, and that's right here. So in Draw, we're going to set our background to the highest intensity in black. You can play around with this and do whatever you want with it. The next thing we want to do is we want to set sound wave equal to the return of this Fourier transform using the analyze method that's associated with it. So this constructor has some methods. We can use analyze, or we can use, well, I think it's waveform is the other one. So those are your 2 different data sets that you can extract from your sound wave. We're going to use analyze because it returns a nice, easy to use set of values that we can that are mapped well to the sound in a way that we can use that visually. So once we have our sound wave, now this is now an array of values, and if you notice down here, when I use the values in this, the return of these, I have to tell it which element number to use, so it works just like an array. We're going to translate to the center of the screen so that our origin 0, 0 is in the center, and then we're going to set our stroke, because down here we're doing a begin shape and an end shape, and we're going to set our stroke and stroke weight for that shape at the beginning of this isolation. And we don't want to fill those shapes. The next thing we're going to do is a loop. We're going to loop through all of the elements in the sound wave. So whatever this analysis has returned, the 0 through 63 values it's returned that contain a number between 0 and 255, we're going to loop through those 64 values. So I here is an index value associated with the element inside the sound wave, which is a return of this fast Fourier transform. Inside that loop, we're going to do our begin shape and end shape. I'm not sure why they're... Oh, yeah, I do know why they're inside. If we put these outside, all of the lines that we make inside are going to be joined together. And if you look at the output here, you can see that it's a box is drawn, and then that's the end of that shape, and then another box is drawn, and that's the end of that shape. To break things up like that, we put the begin shape and end shape inside the loop. If you want them to be all connected by a line, then you'll put the begin shape outside the loop and the end shape outside the loop at the end. So we're going to put them inside because we want these nicely delineated. Then we're going to set to a local variable the element value, whatever that amplitude value is, 0 through 255, for that particular element from this loop. We're going to set that to the value amp. Then we're going to call inside our visualization function the method update, and we're going to give to it what element it's on, and then that element value. It's going to get passed into the array. So that's how we're going to use the data from the sound wave analysis to affect whatever parts we're on in our visualization. So the visualization is being activated from 0 to 64. So it's actually moving across the screen. It all looks like one thing, but these pieces are being created individually inside the loop. And then once the loop's done, it's displayed or it's output. So even though it looks like it's happening all at like one time, one frame, it's multiple frames that this single wave incident is created. All right, then we end our shape inside that loop, and that's the end of draw. Next, we're ready to jump to our visualization. In the global space of our visualizer, we have a few variables that we need. We need one that will control that will normalize the amplitude. So it's a value between 0 and 255. And we could use that range graphically, point for point. But if maybe 255 is too long of a line or too big of a box, then we need a factor to adjust that by. And I always want that to be in ratio to the screen proportions. And I use the height always because it's the least of those proportions. So I'm taking height and multiplying it times a fraction. And then I'm going to take this value, and that's going to be the range of the size of things. Next, we want to create the sinusoidal wave in the substructure. So this part is getting ready to bend right now. And then next, now it's going back in the other direction. Doesn't look like a wave is happening, but it's at a nodal position in its waveform. So it kind of slows down in that part, hovers around that node, and then it moves quickly along the waveform. This wave is moving back and forth, and once it reaches so far, once it expresses so many frequencies inside this wave, it stops and goes back the other way. That procedure is controlled by these two variables here. So this is this is what is actually moving or controlling the frequency of the number of waves. That you can see there's 3 there. Then there'll be 2, and then there'll be 1. So that's because this number is going up and down. And the speed that changes is controlled by this variable here. So once we have our global space, our initial setup variables, we can jump to our method inside this function called this.update. We're going to receive 2 variables, and I'm going to call it visualization I and visualization amplitude, or VIVAMP. I'm going to use a global variable to assign x, to give us our x position. And basically it's pretty straightforward. We're moving from one side of the screen to the other, determinant of the index value. So index value 1 gets the furthest left position, and the last index value gets the furthest right position, and they're all evenly distributed in between. That's pretty straightforward. And we do that with an interpolation. We basically take the index value of the spectrum array, which can be a value between 0 and I think it's actually 63, which will return a location between negative width divided by 2 and width divided by 2. And since our center, our origin, 0, 0 is at the center of the screen, half of the width negative will be the left side, and half the width positive will be the right side. Just to keep things handy, I wanted to have a frequency value. So how many of these things are there? What's the distance between here and there? We can work that out, but we need a variable that makes it a lot easier. So all I did was take the total width of the screen, and I divided it by the number of bins that we have available in the amplitude. And then that gives us this distance between these rectangles. I'm not sure if I use it in here anywhere, but yes, I do. I use it down here when I adjust the vertex. Because I'm drawing a rectangle using draw shape instead of just drawing a rectangle, which seems like it'd be so much easier, I need to know what the actual width is that these things are, and that's what XF is. So another local variable, y, is another interpolated value, and this is basically the height of those boxes. So I can use the amplitude value to tell me how big those boxes are. So this is where the feedback from the data plays into the visualization, because we're using this changing amplitude value to define how big these rectangles will be, how tall they will be. So as the amplitude changes, these rectangles will change in size, and if it's a rhythmic change, we'll get to see these bounce rhythmically. The size of that box, that rectangle, is determined by that variable that we set up here to begin with, which is a fraction of the height. So next we want to advance the substructure, the sinusoidal wave. Let's advance the value that's used to compute how the wave is drawn. We're going to advance that by this velocity value. But if you find that the movement is too fast, you can add just multiply it times a coefficient, or you can adjust this up here. Either way, it just depends on if you're using this value somewhere else and that speed looks good, then you don't want to change this. You would use the same variable and just multiply it times whatever you need to make that other thing move a little bit better. So that's what is happening here. And then I want to bounds test that. So if it's outside of a certain range, then I just want to flip the velocity. So if it's moving positively, let's multiply it times -1. So now it's moving backward. And that's what this is doing. The ranges here are kind of arbitrary. It's just how many waves, how many of these, what frequency do you want this sinusoidal wave to max out at? If you have too many waves cramped together, it loses its wave form, so it doesn't look as obvious. It looks more chaotic. So just a few waves in there is fine, and I found that to be about 350 and -50. You could have it go backward the same amount. I have it step backward not so much, just a little bit, and then go forward a ways. So it hovers around that flatness, because that's like the nodal frequency for that wave. It hovers around it a little bit longer, and that's just a stylization thing. So play around with that however you want. So in order to get the sinusoidal wave to apply to the Y positions, I need a modifier. So that's what this is. We're going to use a local variable called YMod, or Y modifier, and we're going to use a sine wave, and we're going to put the math for that sine wave frequency value that we're advancing here. We're going to put all that in here. And you can play around with these variables to get different speeds and different movements, more customization, something that maybe matches the music a little bit better. If it's slower music, you might want slower moving waves. If it's faster music, you want faster moving waves. That's what you can do here. The return of the sinusoidal wave is -1 and 1, and you just map that to the height times a coefficient. And this could be the same as, or close to this one up here. So just play around with that and see what you like. Once we have all of our variables, we're ready to put those in the coordinate system for our shape that we're making. So we're using vertex to tell p5.js keep track of this shape in a table, and then make the shape using these coordinates in order. So the first vertex is the lower part of this. No, it's the top left corner is the actual plotting point for that waveform. And then this rectangle is built off of that single point. So I'm starting in the top left corner, and I'm going down so far, right here. Am I going down? Maybe I'm going backward. I don't even remember how I did this. Anyway, you can kind of work this out if you're familiar enough with drawing boxes and what it looks like mathematically or in a coordinate system. This is it. I'll explain the modifiers here. I have XF right here, which is adjusting where this... what is XF? Oh, yeah. XF is the distance between this box and that box. Trying to remember what I just said 5 minutes ago. So I'm adding these two coordinates correspond with the far side of the box. So this far line would be that. And the Y modification is controlling how far up and down these are moving along that sinusoidal wave. We isolate those in push and pop. I'm not sure where the push is on this. Oh, here it is. Yep, push and pop. If we put anything else in here, which we can do, you can add lines, you can add all kinds of stuff, which you'll probably want to do. This container is going to allow you to do that without changing the global settings for the graphics attributes. And that's the end of the function and that method. And then down here is the toggle music in the global space, and it just uses the method pause and play associated with the variable that's holding your music file. It's that simple. So that's pretty much it for this part. So here at the end, one of the things I wanted to talk about is, so now we have this wave here, and we have it moving up and down. And it pretty much looks like a sound meter, a digital sound meter, like on an old-timey cassette player. You know, sometimes the boom boxes, kids might remember those. They would have this readout, and this is kind of what it looks like. And it's not very compelling, actually. I mean, you can kind of tell the music, what's happening. But as far as interesting, it's really not that cool. So I'm going to play, I got another one here that I'll open for you, which maybe we'll do this in another video where we'll add on to it. Okay, so this is the same sort of setup. I'm still using the substructure, but now I've added rotations to that substructure. So each one of those rectangles that was floating on those bars, imagine if it was spinning around the location that I'd plotted it at. That's what's happening here. And instead of drawing boxes, it wasn't too hard to make musical notes. It's just a point, a line, and another line, but with a wider thickness. And you can control the thickness and set that to spikes in the beat. So you can look at the amplitude, and when you see spikes, maybe something that's above 100, then move the stroke weight. And the end result is that the stroke weight of these flags on the eighth notes, I guess those would be eighth notes, they are getting bigger and smaller. They're kind of jumping to the beat. And then you can use some lines down in here. I'm not really familiar with how to use these. I'm getting better at it, but it was a learning curve. This Bezier line has 4 coordinates, and it can create these loopy lines that are pretty fun to play with. This is a really flattened out one. It's not looping in the center, but if you increase these values and bend these arcs, you'll get loops that form, and that can be interesting. But my intention was to make these as like the score, musical score, or maybe the piano strings or harp strings, and you can see that their location, their folding, their bending, the values of this Bezier curve is controlled by the amplitude. So there's a feedback between that amplitude value and how this line is being produced. And we're going to play it. I think I just quit. There we go. Play it again. And so there's lots of stuff that you can do that is custom to the music. It's really hard to make a visualization that's one size fits all. You can, but it's not going to be very compelling. It's not going to be very interesting, and it's not going to accentuate the music. So one of the things that you might find interesting when you're making visualizations is to just really customize that visualization for that particular song. Kind of making a music video for that song, in a way. When you are customizing it, then you can start putting in place conditions that fit those amplitudes and those frequencies more precisely, so that certain crescendos, certain softnesses can be responded to. You can identify that in the data and respond to that visually. So visualizations aren't something that easily comes out of the data on its own. It's more of something that you have to work with. You have to look at it and listen to it and try to find out where in that data are things happening that I can respond to with procedures that's going to make it more compelling and more fits like a glove kind of visualization. So that will be the next part. You can see here this is kind of a step toward that. But this is a learning process for me. Visualizations is something that I've always wanted to do since the 90s, since I first saw them on old SX computers. I thought they were amazing, and I wanted to learn how to do the ones that I saw. I had been doing visualizations before, but they were just data visualizations. It wasn't music data, because it was pretty much out of the question given the hardware that was available in the 80s and 90s, early 90s. It's not until today that I'm really able to use the tools, and that's been really helpful. It's advanced it. It doesn't seem like it's as difficult to plug into these things and get the data that you need and respond to that data with procedures. It's a lot easier than what I imagined. So getting the p5.js sound methods and constructors and understanding those, that's one thing. But then once you have those tools, you suddenly realize that that data isn't as clearly presented as you might want it to be. It's very raw. It has to be cooked a little bit in order to get these ingredients to make something that's going to be really palatable. So that's what I'm going to describe in the next video, or maybe two. How do we get from p5.js fast Fourier transform returns to an interesting visualization? So I hope you'll join me for that. If you've enjoyed this video, if you've learned something from it, please give me a like, a thumbs up. And if you haven't subscribed, I would be honored if you would subscribe to my channel and follow along, and let me know what you think, if it's helping you out or not. I guess that's it for this one. Until next time, as always, take care.